Hi, welcome to another sessions of Circuits and Networks. In today's class, we are going to deal with resonance in parallel network. As you can see, the parallel circuits, the passive elements, they can be given across AC supply, either in this fashion or in this fashion, or the combination of all the possibilities. So we are going to see in detail how the resonance circuit can be solved for parallel circuits in different arrangements. So in our previous classes, that is in series resonance circuit, what are the important points which we have derived is we have seen the bandwidth and we have seen the impedance where W naught is the angular resonant frequency, W1 represents the lower cutoff frequency, W2 represents the upper cutoff frequency in terms of angular, and they can be changed to normal frequencies as F1 and F2 and the resonant frequency F0, and the current waveform under series resonance, it is obtained in this fashion where you have minimum impedance. When you look at the impedance graph, when the impedance is minimum, naturally we are going to get the maximum current. So the maximum current is obtained as V by R, so which indicates that under resonance per series RLC circuit, the complete circuit behaves as purely resistive, and that is how we have obtained the maximum value of current. When you going to look into the formulas, the angular resonant frequency is obtained as 2 pi f naught, where the inductive reactance is given by 2 pi f naught L, and the capacitive reactance is given by 1 by 2 pi f naught C. The resonant frequency for series RLC circuit is obtained to be 1 by 2 pi under root LC. The bandwidth, which is nothing but the difference of upper cutoff frequency to the lower cutoff frequency, is obtained to be R by 4 pi L, and you can also determine the lower cutoff frequency value with f1 is equal to f0 minus r by 4 pi l, and f2 which is equal to f0 plus r by 4 pi l. With all these derivations, we have determined the quality factor under series resonant circuit, which is equal to 1 by r under root of l by c. So this is the important formulas which we have derived in our previous classes for series resonating circuit. Now the same thing we need to find out for parallel circuits under resonance. So resonance, it is defined in many ways, like in which the inductive and capacitive effects neutralizes each other, or the power factor of the circuit will be unity. Therefore, impedance of the circuit becomes resistive. The input voltage and the input current are said to be in phase under resonance. So the phase angle between the inductive and capacitive will be equivalent to 0. So it describes the phenomena of energy transfer between inductor and capacitor. And the resonant frequency is defined as the frequency at which the energy is transferred between an inductor and capacitor. So for parallel resonance, we have the parallel circuit in this fashion, either in the impedance of ZA or ZB, and ZA can compose of the passive elements in the different forms. Similarly, ZB also can be have the passive elements in different forms. So either you can have this kind of arrangement or you can have this kind of arrangement. In general, for the impedance calculation, we formulate the impedance in parallel circuit as 1 by Z is equal to 1 by ZA plus 1 by ZB, or in fact you can get the parallel combination to be the impedance value equal to ZA ZB by ZA plus ZB. So this is how we have to concentrate on impedance of the circuit. Once we are obtaining the impedance of the circuit, then it is easy for us to obtain the resonant frequency of parallel network. So let us go with an example. You have resistor, you have inductive reactance, you have capacitive reactance, and the series combination of R with L is arranged parallel with XC, which is capacitive reactance, and it is supplied by input source. So here you can take the value of impedance 1, which is equal to R plus jXL, and impedance 2, which is equal to minus jXC. Since it's a capacitance, so Z2 is equal to minus jXC. Now the admittance of the parameter will give you the value of Y1 under Z1, which is equal to 1 by Z1, and just substitute the value of 1 by R plus J XL. Just rationalize this value and we are going to obtain the value of Y1 to be R minus J XL whole divided by R square plus XL square. Similarly, obtain the value of admittance which is equal to 1 by Z2. Substitute the value of Z2 here and we can reframe this value as J by XC. Once we obtain the value of Y1 and Y2, it is easy for us to obtain the admittance value for the parallel circuit which is equal to Y1 plus Y2. Just substitute the values of Y1 and Y2. So we are going to get R minus JXL whole divided by R square plus XL square plus J by XC. Now when you take the real values and the imaginary values on one side, then this is how the admittance parameters is going to be. Now this will give you the conductance value and this will give you the susceptance value. Like in the case of series resonating circuit, we have the real component which is resistive and the imaginary component which is inductive. Similarly, under parallel circuit, we can frame the impedance with the admittance value. Under real value, it will be conductance and the imaginary value will be the susceptance. I hope you understood this equation framing. Now, under resonance, the susceptance value should be equivalent to 0 because the imaginary value we have to equate to 0. When you are going to equate this value equivalent to 0, we are going to left over with XL by R square plus XL square is equal to 1 by XC. Just cross multiply on both sides. We are going to get XC equal to R square plus XL square. So for this value, just substitute the value of inductive reactance and capacitive reactance. So under angular frequencies, these two terminals will go off and this XL is replaced by omega naught square L square. With this, I'm going to get the value of omega naught square L square is equal to the L by C minus the R square. In fact, omega naught square is equal to 1 by LC minus R square by L square. So with this, we can go easily derive the angular resonant frequency which is equal to under root of 1 by LC minus R square by L square. So with this, we can derive the natural resonant frequency whose value is nothing but F naught is equal to 1 by 2 pi under root of 1 by LC minus R square by L square. Now this is pertaining to this combination. This resonant frequency is pertaining to this combination. So it keeps on changing with the changed value of inductive and capacitive arrangements. Now once the R value is less, so you can ignore this value and we can reframe this omega naught which is equal to 1 by under root LC and frequency is equal to 1 by 2 pi under root LC. For lower values of R, this can be neglected. So with this, we can derive the quality factor which is nothing but the ratio of the current across the capacitor to the current across the resonating circuit. So with this, you can substitute the value of the current across capacitive to the resonating current across the element. So which you are going to obtain the value of Q naught to be omega naught C by CR by L. So this is nothing but omega naught L by R. So when you are going to substitute the value of omega naught in terms of 1 by under root LC, you are going to obtain Q naught to be 1 by R under root LC. Now this quality factor, it pertains to the value when the resistance is of small value. Otherwise, the quality factor will also change according to the given value of the resistance. So in general, for the low values of resistor, this is the quality factor for parallel resonance when the arrangement is in this fashion. So this quality factor, bandwidth as well as the resonant frequency, they all get changed based upon the arrangement of the passive elements in parallel arrangement. I hope you understood this derivation. So here is an important factor is that what is meant by dynamic impedance. So like in the series resonating circuit, we have estimated the graph for impedance as well as the current. So here under parallel resonating circuit with RL in series parallel to capacitor, the resonant frequency is given by F naught and the current is assumed to be the minimum value because it's a parallel circuit, so the current gets divided in general. So naturally the current value will be the less under parallel circuits. So F naught will be the resonant frequency where you have the minimum value of current. When you have the minimum value of current, naturally the impedance of the circuit will be the maximum. So this is the derived waveform under small resistance when they are arranged in parallel networks. So here I naught value is nothing but V by ZD. ZD is defined as dynamic impedance. So the dynamic impedance is equal to L by CR. So how this value is obtained? Because at resonance, the total impedance of the circuit becomes resistive, and since the real part of the admittance is given by R by R square plus XL square, so this is the impedance value. So this is the reciprocal value of the impedance because it is stated as admittance. So dynamic impedance of the circuit will become reciprocal of this value, nothing but R square by XL square, R square plus XL square by R, which is nothing but the dynamic impedance of this parallel arrangement of R in series with L parallelly arranged to the capacitor. So at resonance, we know that XL XC is equal to R square plus XL square. Just substitute the value of uh, XL and XC, then we are going to obtain the value of the dynamic impedance, which is equal to L by R. So this graph also you can plot with the basic equation. So this is how we have to understand the combination of parallel passive elements under resonance. So this arrangement can also be modified into this fashion. You can see the possible combination, or in this fashion when you have capacitance networks, just you have to remove resistance in order to obtain our original case. So likewise you can have different combinations of parallel arrangement of passive elements. We are going to look into the detail of arrangement of different forms of parallel circuits. So this is the basic class what we have dealt with parallel resonating circuit. So in today's class, we have seen about the resonance in RLC parameter, the basic form of arrangement. So I hope you understood this particular video. In next class, we are going to see some of the numericals pertaining to RLC parallel network. So I hope you like this video, share among your friends and subscribe to my channel, and please press the bell icon for the future notifications. Thank you.